Hello everyone, I am AJAY JAISWAL, a second year PhD student at UT Austin. I'll be presenting our work, Attend Which Week, Pruning-assisted medical image localization under sophisticated and implicit imbalances, which is done in collaboration with Dell Medical School and Well Cornell Medicine. Deep neural networks has rapidly become a de facto choice for medical image understanding tasks. However, DNNs are notoriously fragile to the class imbalance in medical image classification, and it amplifies when it comes to more sophisticated tasks such as pathology localization, as imbalance in this task have highly complex and implicit form of presence. For example, different pathology can have different sizes or colors, different underlying demographic distribution, and in general, different level of difficulty to recognize them, even in a meticulously curated balanced distribution of training data. The main inspiration of our work is drawn from a recent study by Sarah Hooker's team at Google that the deep neural networks have difficult to memorize samples, and these may be effectively exposed during the network pruning. DNN optimization is content-aware, taking advantage of the patterns shared by more training examples, and therefore inclined towards memorizing the majority samples. Since minority samples are underrepresented in the training dataset, they tend to be poorly memorized and more prone to easily forgotten by the model after pruning. In this paper, we attempt to ask an interesting question: can we identify instances which are difficult to memorize by deep neural networks, and can they act as a representative of complex and implicit balances? We propose pruning as an indicator to expose the spatial weakness of trend localization model and show the existence of hard-to-learn training samples. As shown in the figure, our work revealed that pruning disproportionately impacts the foreground and the background classes, whereas the foreground performance of some training examples can drop by a much larger margin than the background, indicating higher sensitivity to the pruning. Tailored to the localization task, we present three novel, hard-to-learn mining strategies in supervised, semi-supervised, and weakly-supervised setting, using our ground truth labels, pseudo-labels, and saliency map respectively. We additionally show that attending HLTs by fine-tuning, one can significantly improve localization performance. The figure in the slide illustrates the overall pipeline of our HLT mining technique, followed by additional fine-tuning of the network to focus explicitly on those examples. In the next section, we will briefly present our results. Table 1 represents percentage drop in IO of the training samples in the disease localization task when the trained network is pruned by P%, using the unstructured magnitude-based pruning in supervised and semi-supervised setting. This proportionate impact of pruning can be clearly observed for the background and the foreground classes. Similarly, figure 5 illustrates the example of the visualization of segmentation masks generated by baselines, which can be found in our paper and our methods on HLT samples. With additional attention to the HLT samples in fine-tuning, the model is able to generate better segmentation masks for HTLs, improving the overall performance. To illustrate how HTL-aware training will benefit the overall performance, Table 2 illustrates the performance comparison of our methods against different baselines. In addition, very interestingly, an in-depth analysis of HTLs using demographic attributes such as gender and age revealed that pruning impacts some of the demographics more significantly than others, diligently eliciting the complex and subtle imbalances in the data going beyond the class distribution. For more algorithmic and experimental details, please visit our paper. Thank you very much for your time.